so that is your lac operon. That is the inducible one. Yes?
So after the lactose combined into the suppressor, causes the suppressor to change shape.
Yes.
What's after that?
The suppressor changes shape. It can no longer bind up to the operator. Therefore, it can no longer prevent the RNA polymerase from reading DNA.
It can no longer read DNA.
It can no longer stop the RNA polymerase from reading the DNA. Therefore, it's going to be read, it's going to be expressed, it's going to be translated, it's going to be made into the enzyme that will then be able to work on the lactose in its environment. Now, let's look at your repressible ones.
That's still the number 9?
Huh?
Yeah, those are your years.
So, once again, you have your,
The repressible ones.
So
Yeah.
this is the trip operon?
yes.
Okay.
So, you have the same thing here. You have an operator. You have a promoter. And you have your regulatory gene. Right? But this one is normally turned on. And it's normally turned on and is going to be producing tryptophan, right? So,
How do you spell it? Okay, keep going.
okay. So it's being transcribed. So you get your RNA. And you get your protein from it. Okay, so now you get your protein. And that protein, or here in this case, we're talking about the amino acid. The amino acid tryptophan.
It's being transcribed into RNA and then what?
It's being transcribed to the RNA and it's producing tryptophan. Okay? So now you have all these molecules of tryptophan and they're accumulating. Okay? So normally this is producing an inactive form of this.
So usually for
It's producing it, but it's inactive. Okay?
The amino acid tryptophan?
This right here is a regulatory gene. The regulatory gene is producing an inactive form of the suppressor.
So it's usually producing an inactive form of it?
Yes. It's producing inactive form of the suppressor. So this one here would be your promoter. And this right here would be your operator. Okay? So this is inactive. But remember how we talked about the feedback loop? When you have an overproduction of something, it's going to then act as a allosteric inhibitor. So this tryptophan that is being produced in mass amounts, now it's too much, it will start to come over here and bind onto the inactive form here, converting it into an active form. Notice there's a change in shape there, right? And so this active form will come up to here and bind onto the operator. And when it binds up to the operator, it does not allow for that gene to be expressed. Okay.
So, wait, thereafter you said it combines with the inactive one and it turns it into an active
Yes, now it
Suppressor
is,
and then what?
this one here is now active.
To an active form and then what?
Now the active one will bind unto the operator. Right? The operator that's been bound, so now your RNA polymerase will not be able to bind onto there, and you will stop transcription. You see that? Tryptophan is being constantly made because this is on all the time. Well, when that tryptophan is made in abundance and too much is made,
So the buildup.
it will bind onto the inactive suppressor, causing it to change shape. It is now active. In its active form, it can bind onto the operator. When it binds onto the operator, it prevents the RNA polymerase from binding onto the operator or reading through on the operator because it's going to bind the motor. Anyways, so it may bind onto here, but it will not be able to read, so it will be kicked off.
So it prevents the.
It prevents the transcription of that gene. When it prevents the transcription of that gene, none of this stuff happens.
Okay.
That is
Question,
done.
you had this slide, the protein, you had the amino acid tryptophan, why?
This is always turned on. Its job is to produce
Okay, but
tryptophan.
why do you have protein, the word protein in there? Is that what it means?
Proteins do a lot of different things. Proteins are inhibitors. Proteins are carriers. Yes. What?
My question was, okay, besides proteins, you had amino acid tryptophan, why?
Because that's what it's producing.
Okay.
Its job is TRP, stands for tryptophan. Its job is to make tryptophan. When it makes tryptophan in too much amount, it will then cause it to be inactivated, kind of a feedback loop. Negative feedback.
The tryptophan, can you just say tryptophan binds with lactose? Is that the suppressed? No.
There's no lactose involved.
Oh, there's not?
Nope. Okay, so now describe the cause and outcome of 3 other types of mutations we discussed: silent mutation, missense mutation, and nonsense mutation, as well as the frame shift. And with the frame shift, we're talking about insertion and deletion, right? So, if you were to go to your PowerPoint on chapter 7, wherever it comes up. And it talks about mutations.
Like radiation, chemical mutation, all that. Those would be the causes.
Yes, okay, so there is a thing in here that talks about, I believe it's on plate 66, figure 7.24. It describes what's going on with a silent mutation, a missense, and a nonsense. And then what happens with the frame shift, okay? With a silent mutation, what occurs to make the mutation?
The gene is not the same, but it's still different.
Okay.
Different amino acids, right? Amino acids.
It's going to, no, it's going to create the proper amino acid, but the wrong code was there. So you're going to have a point mutation, meaning one nucleotide is going to be wrong, right? One nucleotide base, I should say, base pair, is going to be wrong, right? Because of that one mistake, a different codon is going to be made. But because of redundancy, that means that we can have one amino acid made by 2 different types of codons,
Yeah.
or 3 different types, or 4 different types. So in case there's a mistake, the correct amino acid can be made even though it's a different code, right? So it's silent because the correct amino acid was made. If the correct amino acid was made, the sequence of amino acids that make up that protein are the same, meaning that the correct protein is going to be made. So the correct function can occur. That is silent. Nothing bad happened even though something bad happened. Okay? Now, with a missense. With a missense, you're still going to have a point mutation that occurs, right? A different nucleotide or nucleobase is in there. Now, as that protein is being made, the sequence of amino acids is going to change by 1 amino acid. That means that everything is correct up to this point, but those 3 letters of the codon are going to code for a completely different amino acid. All the rest of them are correct, so it's going to code for the correct amino acid. So the chain is going to be the same, all except for that 1 amino acid. So I still get a protein made, but it's the wrong protein. Okay? So that's what's meant by nonsense. I can still make a whole protein, but 1 amino acid is off. If 1 amino acid is off, it's a completely different protein. Okay? It does not have the same function as the protein that it should have been. Now, with a nonsense, what happens with a nonsense mutation is you have that 1 nucleobase that is wrong, but because that 1 nucleobase is wrong, the codon is going to be a stop codon. So I may have the correct sequence up into that mutation, but because a stop codon is coded for there, then nothing else will be made. Okay? The protein is not going to be made. If I don't make this protein, then it could be deleterious for the bacteria or the organism, right? It's not going to make the protein at all, or any protein. That's nonsense. Well, to them it might be nonsense. To us it might be good. Now, frame shift. Frame shift mutation can be caused by 2 different things. What are those 2 different things? One could be in an insertion, right? And one could be a deletion. So we know that the DNA is read in sequence, right? But what happens if I insert a completely different nucleotide in there? That changes the whole way that that frame is going to be read. So I'm reading everything correctly up to the point where that's insertion that shifts how that frame is read. So those 3 codons are going to be wrong. And that's going to give you a very different, major difference in the amino acid sequence. Okay? Same thing with deletion. I have a set code that should be there. If I delete one of those nucleotides out of there, that changes the way that frame is read. So it's, again, a frame shift. The resulting amino acid sequence is going to be majorly different because that's the same thing as if I'm reading everything correctly here, all of a sudden I don't have that nucleotide there, but so I'm going to read the next 3. Those next 3 may be wrong, or not maybe, they are going to be wrong, right? And so the whole way I read that frame has been shifted. And so it's going to produce a major difference in amino acid sequence. Okay? What is the next question?
Oh, we already did that.
We already did? Well, we went over. What was it?
The rat one.
Okay. And we actually did that one in the lab, right? Sort of. That's transformation, right?
Bye, guys.
All right, bye. Hey, tomorrow, 10 o'clock at the coffee house, we'll have another review if you guys have a chance. All right. if you guys have not taken pictures of